So what? First of all, hi everyone. Uh, Thanks for the invitation. Obviously, Professor Wakala, really nice for inviting. And yeah, as I can anticipated, I'm a PhD candidate at the University of Birmingham, and I'm working in collaboration with Marta Mazzocco. And what I'm going to talk about today is really based in full details in this paper we posted recently, and hopefully we'll see it published quite soon. So yeah, let me kind of break the ice by getting everybody on the same page, at least with some of the jargon I'm going to use, and let's say in the broadest possible terms, the area I work within. So for me, quantum algebras are first and foremost non-commutative algebras, and the way they are quantum is really in the deformation sense. So you have to think that you start with a more classical, more familiar, I would say, algebraic object, and you deform it with a parameter, typically it's q. In this talk, it's going to be a q, in such a way that using some physics jargon, the classical limit that for q typically is q going back to 1, you recover your starting object, like the more classical one you started with. And typically these deformations add some sort of further layers of non-commutativity to your original object. Now, this is, let's say, broad enough, a kind of playground to encompass the whole of, let's say, quantization framework for more classical algebraic geometry, in the sense of thinking about coordinate rings for non-commutative algebraic spaces. So that's good, considering how it's like this kind of quantum algebra is developing these days. And in terms of some influential examples, you clearly can think of the law of quantum groups. If you're more kind of diagrammatic, categorical in spirit and taste, you can think of, say, templative algebras. Or if you're more into kind of realization of quantum algebras in analysis, say, orthogonal polynomials, special functions, you can really think of double-affine-Hecker algebras, GDAHA for short. Now here, at the bottom of the slide, I kind of put what is probably the most prototypical example of a quantum algebra, I would say, in really this kind of quantum geometric perspective. So we're going to start with the coordinate ring of, let's say, an algebraic two torus. So we get polynomials of Laurent type into variables, and the deformation that lends you the so-called quantum torus is now a free algebra into invertible variables modulus this Q commutation. And you can clearly see that the classical limit is really manifest in this very prototypical example. Not only this prototypical, but on the other hand, this is really kind of the building block of like more kind of convoluted quantum algebra we'll see popping up later that will essentially be higher dimensional quantum tori. Good. So before really outlining kind of the plan of the talk, I want to kind of get you all, at least very quickly, it's going to be a crash course, introduced to the special kind of class of quantum algebras I worked on that goes by GDAHA for short, which is generalized double-affine Hecke algebras, and we'll see like generalized in which sense at least. So there is one such algebra, one such GDAHA, that I denote H indexed by D, out of any of 4 affine linking diagrams you see here. So what's special about this? Well, there are affine linking diagrams, so they come out of the theory of the affine, the algebras. So they're, at the end of the day, like the usual linking diagrams, but you just add another node in a certain suitable locus, say because of D4. And any of these, like verified ones, can be thought of the other one. And on top of that, they are simply laced, so you can't have multiple edges between 2 nodes. And moreover, they are star-shaped. They're so-called star-shaped. They have like a central node, and the others radiates as like a... Now, these are quantum algebras in a kind of framework I introduced before. So first and foremost, I want to start with a more classical object and realize these algebras as some quantum deformation. So the actual object we want to start with is a group algebra. And the group is essentially kind of indexed or kind of encoded by the diagram. And it is a planar crystallographic group, which means that you have to think of some lattice in the plane and study symmetries of it. So being lattice on the plane, there's always the freedom of translating it. So you see there's always a component set squared here. But then you can, according to the shape of the lattice, have either reflection and or rotations. And so you have like another component in this kind of semi-direct product realization of the group. And for these specific diagrams, you restrict only to rotations of a certain order given by the length of the longest leg in the diagram. So you see these are the legs, and you count them in terms of length by just counting the nodes. So for this case, they're all length equal to 2. For this case, all equal to 3. In this case, you get length 4. In this case, you get length 6. And so you get a cyclic component here of the order equal to this longest length. So let me kind of introduce you to the actual GDAHA of type, let's say at least in the case of D4 as a sort of reference. So in this case, components are Z2, so they're involutions. And indeed, the presentation for the group can be given as this. So you get a generator UI attached to any these legs, so 4 generators, they are involutions. Moreover, they multiply to the unit, well, the identity. So this is a starting group. You take the group algebra, and this is your starting, say, classic algebraic option. Now, these are quantum algebra because you start deforming the relations using some quantum parameters. Actually, this is a two-step deformation. So first is like a proper, say, quantum parameter, and this only it's the second one. That's this. And the result of this deformation is really the prototypical deformation we saw in the slide before, in the sense that when I take the group algebra Z squared, I get back to polynomials of Laurent type into variables, and the effect of this Q here is really turning that into the quantum torus. And this is clearly uniform, no matter the type of thinking diagram we pick. In terms of the involution, then we deform it in the really Hecke type way, like how
just a quick question.
GDAHA and affine. Please, yes.
So when you put this cube in, you say you get suddenly the non-commutative torus instead of Z2. Is that, I mean,
Exactly. So technically, this is the group. You take the group algebra of it. So the component here in terms of the group algebra becomes Laurent polynomial into variables. And that component is turned into the quantum torus, exactly in the same fashion we saw in the introductory slide on quantum algebras.
but then
That's the effect of
one
this
when
kind
you
of
expect
deformation.
to get the torus rather than something discrete.
Say it again, sorry.
If when Q is equal to 1, then wouldn't you expect to get back the 2 torus rather than the
But it's a Pontryagin duality. You're looking at the.
Sorry, I didn't see the C of Z2, of course. Yeah, sorry, dumb. Yeah, gotcha. Okay.
No. I mean, please interrupt me anytime. I mean, I'm happy to share what I did, but to make something clear and not something confusing. So feel absolutely free to stop me anytime. So this is the first step. We get to this. Now, we want also to deform the other kind of rotations type equation. And in the case of the involution, this is really the deformation in the usual affine Hecke algebra sense. So we add another parameter for each generator. And again, you see that if you take for this UI going back to 1, you recover the starting relation. So putting all things together, this is basically your very neat and simple definition that you get, at least in the case of T4. So it is a quantum algebra parametric, not only on a Q, but also on a sort of vector of parameters that I'm going to call like Hecke parameters. And this clearly, the second step is adapted according to the diagram in the sense that you get here as many factors as dots of the corresponding leg, and you just need to scale this Hecke parameter with roots of unity in such a way that, again, you preserve the classical limit. Okay, so let me kind of give you a flavor, at least a taste of why these algebras can be interesting and the way they kind of interact with many other areas of not only quantum algebra, but more like mathematical physics at large. Now, first, I want to kind of settle the kind of existential problem for these algebras in the sense that they actually are meaningful in truly the categorical sense, because, well, again, I use HD4 just as a guidance, but everything is straightforwardly generalized, no matter the diagram. So this is a flat universal deformation. So really, like, it's universal in the categorical sense, so this is exactly the object you would expect in terms of deforming this algebra here. Flatness, really, so it's more formal in the original paper. They give a sort of explicit PBW basis, but it's not really polynomial. I'm working on that. So I kind of have a lead to kind of write down specific polynomial type PBW basis. So hopefully this is going to be properly algebraically settled soon. Okay, apart from that, they really are quantum geometric in the sense of what I kind of introduced before. So let me be more precise. If I take a GDAHA and I evaluate it at a classical limit in Q, and I take the center, this is cubic, affine delta surface with like monic leading term. Moreover, any such GDAHA contains an idempotent element that is constructed out of the generator corresponding to the longest leg. And there is an isomorphism, basically telling you that the center is nothing but the spherical subalgebra with respect to this idempotent. Putting two things together, essentially we kind of understand that passing to the spherical subalgebra, we get some quantum algebraic geometric object, because essentially this is an algebraic quantization of the spectrum of this affine delta surface. And that probably is the reason why originally the definition of GDAHA really restricted on these special type diagrams, because it can be shown that for each of the diagram, there is a corresponding delta surface. If I take a random diagram and I run the construction, I don't get the same result. So maybe there is this quantum geometric existential kind of meaning behind the very definition. Let me say something more. So not only taking the spherical subalgebra, I get something quantum geometric, but these algebras themselves are spherical for like a recently introduced class called multiplicative projective algebras. And these are really the kind of building block for a sort of new version of quiver varieties. So maybe you're more familiar with Nakajima quiver varieties, and they are in this perspective additive version. Now we have a recently introduced multiplicative version, and again, we need a quiver behind. So maybe unsurprisingly, HT4 basically spits you out the quiver, which is exactly the quiver behind the Dynkin diagram described in the algebra. And so there is like a very nice connection with basically probably like the state of the art, I would say, of quiver varieties that are indeed obtained by taking some suitable GIT quotient out of these objects. So we get a connection with proper quantum geometry, a connection with some kind of quantum geometry of quiver types. And maybe last, I mentioned this connection, probably more mathematical physicsy in a way. If I study finite dimensional representations of HD4, this can be extended again, on the classical limit of Q equal to 1, I get one-to-one correspondence with solutions of the so-called Deligne-Simpson problem. Now, the Deligne-Simpson problem basically starts like this. You kind of select some conjugacy classes into some group, and you look for a solution of this problem. So in the case of D4, I have 4 generators, so I expect 4 matrices, sorry, and 4, and they have to multiply to the units, picking MI from the corresponding conjugacy class. So in a way, if I take Q equal to 1, is basically asking the product of the generators being equal to 1. So you can maybe see this presence of the identity here. And this is really connected to the study of monodromy data coming out of some sort of ordinary differential equations on the puncture complex plane. So there is a lot of connection with all that kind of mathematical physics business, connection to Pine-Levé theory, Pine-Levé equations of different type. And in a way, therefore, you kind of see that when Q is not 1, I kind of get a sort of quantization of usual monodromy spaces. And this is actually the other part of the work in the paper that we did. But that's probably a story for another time. Okay. So this was maybe just to give you an idea of the connections of these algebra with other areas of mathematics, and maybe kind of justify why we, in the first place, started studying this, and they were originally introduced, and what is kind of the state of the art of the connection. Okay, so a little bit of recap and kind of setting in stone kind of some of the jargon and of the notation for the rest of the talk. I'm gonna really focus on the case of E6, with D4 being some sort of inspiring basic case to kind of extend. In particular, I'm gonna use the letter capital K for generators of D4. You see here, and being everything of length 2, as I give you in the kind of slide before, you expect quadratic Hecke type relations. In the case of E6, I'm going to use capital J, and you see that they get cubic relation because now the length is equal to 3 for all of them. And the Hecke parameters with no superscript correspond to the case of D4, whereas when you have a superscript with kind of parentheses, they correspond to the case of E6. It's just to kind of set down the notation for later on. So where do we come into this kind of general picture of GDAHAs? The state of the art of the theory is kind of a bit fragmented. Let me kind of explain that. The case of D4 is really well understood. And the reason is that this is really not a generalized DAHA in the sense that the way it is presented, maybe it is novel, but the actual algebra that is constructed is isomorphic to a well-known DAHA, the one of type C, C1 check, that was introduced by Sacchi in the late 90s. And it is very well known because it is the one controlling ASCII-Wilson polynomials. So that's a very famous class of orthogonal polynomials. And so they gather a lot of interest in the past. And as such, it's kind of as dry as something can be in mathematics, in the sense that, especially in terms of representation theory, you have a full classification. And you have very nice explicit ones that are faithful, kind of very neat. And the reason this class is called GDAHA is because the actual E-type diagrams starting from E6 are a generalization of this DAHA in this kind of Dinkin diagram spirit. So that's why they kind of are called GDAHA in the first place. However, I mean, opposite to the fact of D4 in which everything is well understood, in particular, the GDAHA representation theory is still quite open for these truly kind of generalized DAHAs, in the sense that there are some existing results using also kind of very hard machinery like quantum D modules and things like that. And there are also some explicit representation. However, and that's the caveat, they only hold for some specific values of the parameters. So for example, Q is a very specific number, or some of the UI, like with the superscript, some of these really are some very specific numbers. So in a way, there is a lack of a proper representation kind of encompassing the full parametric definition of these algebras. And this was the original goal of my PhD, to kind of try to leverage on many different kind of places and playgrounds in mathematical physics to try to cook up something that was able to answer this very question. So to construct first explicit representation of the case of E6 that was essentially asking for no restriction whatsoever on the parameters. And so this is basically the goal of the rest of the talk. I want to introduce you to get this kind of machinery constructed and get to the actual formula for this representation. So this is indeed the plan of talk. As I said, the case of D4 is more like an inspiring starting point. Indeed, among the many explicit representations that I mentioned, there is one such that was constructed by Marta, my supervisor, back in 2018, that is realizing HD4 into 2x2 matrices over the quantum torus. However, this construction was using classical technical theory and some kind of well-known and at this point even abused, usual kind of or familiar quantization techniques, and as such had no capabilities of being extended beyond this very special case. However, in the same time, since 2018, higher technical theory and kind of a special kind of higher technical theory started to develop, and in particular in 2022, we got like a very massive like result and a mammoth paper outlining a whole new kind of construction and of the very state of the art. And that's exactly what we're going to do, basically, using the capabilities of higher technical theory to extend this kind of type of representation beyond classical technical theory that was very limited here, and construct this desired aforementioned representation in this very spirit. So the representation will be 3x3 matrices over a sort of more convoluted quantum algebra with respect to this case that will be spit out of the machinery of higher technical theory. All you see here is basically the rest of what happens in the paper. If I find myself with a bit of time in the end, maybe I can mention something. But at least as a minimal goal for today, I really want to kind of introduce you to this higher technical theory machinery, the kind of derived machinery we constructed, and the explicit construction of this one. So I think that before delving into this is a perfect time to kind of stop if there are any questions at this point. If not, let's dive into this. So this higher approach to the representation theory of GDAHA. So higher technical theory is a very geometric theory. So I'm gonna kind of move a little bit slow here to kind of introduce you, at least give you a flavor of how this kind of geometric construction work, and also kind of starting to move slowly from geometry to quantum algebra. So as you might expect, the starting datum is indeed a geometric object. So the whole theory depends on the choice of a surface. This is a surface of genus G with S boundary components, and you're also allowed to mark down endpoints on these boundaries. Plus, there's just like a technical condition that you want negative Euler characteristic. Now, really, I want to summarize the whole theory in a single theorem, just for the sake of time, and also for the sake of advertising it, really. At the heart of the whole construction is a moduli space. And this moduli space depends on the choice of the surface, and also a certain symmetry is parameterized by a single group structure. And this moduli space is a geometric structure. First and foremost, is a variety. And not only a variety, but it's a Poisson variety and a cluster variety at the same time. And this construction, this structure of like a cluster Poisson is canonical. So you have a Poisson bracket on the space of functions, and these functions are endowed with a cluster structure, which means that you can take cluster mutations and enjoy all the nice properties that are typical of cluster algebras and are making them so popular these days, I guess. On top of that, you have a huge group of symmetries, both from sigma itself and like its geometry, and obviously from the group itself. And this big group of symmetries is acting in an equivariant way, so you cannot commute this Poisson structure. Now, really, this sentence is basically the very essence of the theory, because it's really encompassing most of the kind of serendipitous and fantastic properties that these moduli spaces have. In particular, the whole kind of advertising I want to make here is that by this very sentence, this moduli space becomes a sort of very strong candidate for a sort of geometric realizer of quantum algebraic objects. In particular, for example, quantum groups can be realized by picking a certain geometry sigma and a certain group G, really in geometric terms within this moduli space. But probably the most maybe appealing fact is not only that you realize the algebra within the moduli space, But in a single shot, using all this canonical equivariant structure and the symmetries, you really encode in a very geometric, transparent way the properties, in a way, the whole theory of that quantum algebra. So in particular quantum groups, you can see that all the nice properties of them are encoded into this structure. Please.
So just as a C-star algebraist that's a gumbo about some of this stuff,
Ooh.
when you say quantum groups, what exactly do you mean by that? The specific kind,
Absolutely
like
fair.
Jimbo, or?
I stick to, maybe you would call them on the Hopf side. So just algebraic.
So Hopf
And
algebra is
indeed,
the unit.
But I
yeah,
guess
exactly. On the Hopf side of things.
you're talking about Drinfeld Jimbo, I guess, no?
Yes. So UQG.
UQ.
So the forming the universal enveloping algebra of semi-simple
standard
algebras, indeed.
standard deformation. So then I'm just usually when you say,
Exactly.
since we're asking questions, usually when you say a moduli space, you've got it's an index set for some geometric structure. What is this the moduli space for?
So you pick
Complex structure.
So you get some local systems. So let me just say some jargon. So it is actually the moduli space of local systems on this surface of G-type. And
what's a local system?
Right. So local system is a locally constant sheaf on which you have a G action. So in particular, you kind of think of like linear systems of things. And there is like, pardon?
A locally free sheaf upon which you have a G action. So it's basically like an equivariant vector bundle.
Indeed. So I'm gonna kind of give you an explicit definition of what it looks like for like some more familiar hands-on choices. But yeah, the general definition is in terms of local systems, indeed. So like vector bundle with a connection that is flat. And then you make it a moduli space with some, you typically have to make some choices, right? You want it to be nice in terms of geometry. We're going to see one such choice later on, which is basically cutting you a single big connected component. And not only that, the theory is compatible with cutting and gluing of surfaces. So being very geometric, you want, for example, that if I take two surfaces and I compute the moduli spaces and I glue them, I want the result to make sense with just taking the moduli space of the glued surface in the first place, and also in the opposite way. So you want something that is compatible with cutting and gluing. Okay. And so yeah, as I was mentioning in the groups, the idea is that you realize, and as a Hopf algebra in this theory, but not only that, like the existence of PBW bases, the existence of Chevalier generators, and even the idea of the R matrix, they all have a geometric interpretation within this moduli space. So really, in a single shot, in a very simple and geometrically transparent way, you realize the whole theory of quantum groups. And I think that's very remarkable because usually when you are introduced to this, you first get like the idea of what a Hopf algebra is, and then you have to understand how like UQG becomes a Hopf algebra, and then somebody tells you that with different things you have to cook up some R matrix, and then there is this property, and in another magical way there is another thing. Maybe kind of taking a bit out the magic, but in a way making clarity. This kind of theory gives you a kind of all-encompassing geometric approach to that. So that's more maybe on the advertising bit of things. So boiling this down to earth a bit, grounding it, for the rest of the talk, I'm going to pick PSL and R as a group. Reason being, PSL2R is the group that emerges out of classical Teichmüller theory. So the idea is that to go higher by allowing a higher rank. So N now is allowed to be strictly bigger than 2. And for the kind of reason I mentioned earlier, like just a second ago, basically, about cutting and gluing, I can kind of limit myself to this surface. The reason is that this surface is a genus 0 surface with one boundary, so it's like a disk. And then I have 3 map points. this can be equivalently visualized in a topological way as a triangle. I call 1, 2, and 3 the mark points. And if and that's why I kind of put this here. And if everything behaves well with still cutting and gluing, well, I can basically achieve the modular space for any triangulable surface by just gluing together the data of just the kind of elementary fundamental block that is the triangle. So we can kind of limit ourselves to the triangle and then construct the rest by gluing things together. And that's very helpful in developing such a kind of convoluted theory as the one they actually developed. So at the end of the day, picking this triangle and this group, a point in a modular space is nothing but a triple of flags in Rn. So flags are just some subspaces of increasing dimension into Rn in this case. And these are actually complete flags. So we start with like the trivial vector space. Basically a flag is some kind of f slots, and we start from 0. So the trivial vector space, and then they're kind of all nested till Fn, which is Rn. And they are complete if the dimension of Fi is really I. So you can fulfill all possible dimensions of space with subspaces, nested one to the other. And you get a flag for each, say, of the vertices. And on top of that, you also have a projective basis over each side. So there's one special projective basis here, one here, and one here. So this is really what like all the local system, blah, 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 boils down to the case of these choices. So some sort of kind of linear data in a way, some projective basis and some kind of subspaces located, say, on some geometric data of your triangle. Okay, now what I clearly care about is like functions on top of this. So I want to coordinatize this space first and foremost. And this is done with the so-called Fock-Onshov coordinates. And the recipe goes like this. You start with a triangle and you triangulate it. So this is the case of n equal 2. And I triangulated this with. This is the case of n equal 3. I'm content with this because this is as much as I need for the case of the construction of our representation. And you also see that you basically locate a variable on each of the vertices of this triangulation apart from those that belong to the original triangle 1, 2, 3. So let me make this so that you can see the variables. Okay, so yeah, this really is, by restricting these variables to R strictly positive, the definition of the rank n higher Tech-Miller space, at least for the case of the triangle. The reason for which I restrict the values is for modular space perspective. So this is really the, it's called positive kind of type of things. This is the one that kind of cuts you in like the big kind of mass of the modular space, a huge connected components you want to work with. And this is called the rank n higher Tech-Miller space. And this is also the choice that behaves well with the cutting and gluing. But this really achieves the theory you want to get in terms of geometric point perspective. Moreover, we're going to see in a second that the way these variables appear is through some roots. And so the choice of R plus gives you some canonical choices of roots. That also makes the theory kind of neat, consistent. You get rid of ambiguity. Now, my goal is to cook out of this theory some matrices. At the end of the day, I want to construct a representation. And so I want to use the higher Tech-Miller toolkit to get out some matrices as kind of some building blocks to construct some candidate generators for my representation. And this is the case with the so-called transport matrices. And you see them kind of sketched in their effect as T1, T2, and T3. So as I said, there are some special projective bases associated to the sides of the triangle. And in particular, they are associated to oriented sides of the triangle. So in particular, this is going from 1 to 2. That's why the arrow is pointing down. This is from 3 to 1. And just by comparing two bases, I naturally get a matrix by just thinking of a change of basis matrix. This is exactly what these TI are. So T1 is basically sending the projective basis here to the projective basis there. And I mean, accordingly, the other TIs. And these really, anticipate are going to be the building block for the construction of my candidate generators. Maybe let me just give you kind of a quick look of what they look like, and maybe for you to kind of taste the very combinatorial kind of nature of all this business about higher technical theory. You see that variables will pop up in a very kind of sort of combinatorial style, and maybe just point out for the case of n equal 2, it's the same T1, but one is for n equal 2, this case, and the other is for n equal 3. You see that T1 is sending this side, or better, their corresponding projective bases. And by kind of moving this to this, you see that the only variables that are involved here are really these and this, because kind of this base is not involved in the action of T1. I'm just comparing this with this. Okay, so we know now kind of these TIs are really the object that we want to use. However, maybe it's not like unsurprising to think that as I want to achieve a representation of a quantum algebra, I need some sort of quantum matrices to work with. And indeed, I need to quantize this space. Please. Any question? No? Okay, sorry. So I want to quantize the space, and well, we can go back to the main theorem. As I said, this moduli space is endowed with a cluster Poisson structure. And as such, there is a very natural way, a very straightforward way, canonical, to quantize the space of functions. And it goes like this. So you basically construct a quiver, and the quiver has as vertices variables, and as arrows, they're constructed in such a way that you start with any downward triangle, and you run the arrows counterclockwise. And then you complete the rest in a very kind of natural and coherent way, with just a little caveat that whenever an arrow is sitting on one of the edge of like the bigger triangle we start with, they have to be dashed. So this quiver is really encoding what you want to know about the non-commutative features, as you can immediately see from here. So now it's quantum in the sense that my variables are not variables anymore. They become some sort of, if you're more analytic, you can think of them as operators. If you're algebraic, some generators in some algebra. And a priori, they don't commute. And indeed, they commute only if in the quiver, the corresponding vertices have no direct arrow between them. Otherwise, you get some Q commutations, exactly in the spirit of some sort of higher dimensional quantum torus, with kind of the weights corresponding to the intensity of the arrow. So if the arrow is dashed, you get a 1. If the arrow is thick, you get a 2. If you had a double arrow, you would get a 4, and something like that. The result being kind of...
Do you require any, I mean, can Q be any number at all, or are you only asking for real or anything like that?
So it depends on where you want to develop. This is all typically done with C. So Q, I say a priori, is a number. And this is also like the power of this construction. Because typically, when you work with deformations, many types of deformation are only formal. So Q is like a formal parameter, and you work with a formal series, but that's not really physicsy in a way. You would like Q to be a real number, like H bar, when you put H bar equal to 0. And in this theory, this is really quantum in the true physics sense. So Q can be any number I mean, in this definition, it is just abstracted as a central parameter in the algebra, but really just by evaluating at any possible number, you just kind of bring it down to some honest quantization kind of type of theory. So yeah, you get this non-commutative algebra. In the jargon, originally it is called a quantum cluster variety. Again, the idea is that this is basically quantizing a cluster algebra, but a cluster algebra is the coordinate ring of a cluster variety, all in classical algebraic geometric terms. So when you quantize the space of functions with a leap of imagination, you call it as a quantum space, so a quantum variety. It's just jargon. At the end of the day, all these quantum groups are algebras, right? So, all right, whatever. And it is indeed defined just by taking the free algebras over all these possible z's, modding out all these non-commutations encoded by the quiver. And that's probably the reason why this mathcal x is really a mathcal x indexed by q, so really encoded by a certain quiver. This is the quiver in the case of the triangle for n equal 2, and this is the case of the triangle for n equal 3. So now we have developed basically the whole kind of theory of quantum, higher technical space, and in particular, I have at my disposal these D matrices that are now quantum. So the previous kind of coordinates you see here now are proper operators, or let's say generators inside this calculus. And a priori for the triangle, I know how to compute everything with these matrices because obviously the way a quantum torus is defined is obviously having a PBW basis, so I can run all the computations I want and test and check whatever I like. Okay. Good. So now that I have kind of these playground sets, I can really basically give you the machinery we developed that is basically really moving from all this geometric framework to GDAHAs. So we need to start again with a surface. And out of a surface, the first thing we do is to construct the fat graph of the surface. I will tell you exactly what it is in a second. But the point is that by dualizing this fat graph, we get a triangulation. So now that we have triangles, on each triangle, I know that by kind of moving from one side to the other, I can make these T matrices appear. And by doing so, we really develop kind of a sort of map that is sending paths on the surface to actual matrices. We're going to see this in a second, but basically these matrices kind of indexed or say representing in a way paths are going to be the candidate generators for my representation. Now, why this basically machinery we constructed is interesting? Well, because it does exactly what we wanted to do. So if we pick n equal 2, remember we're developing the theory for PSLN, and PSL2 is the case of classical technical theory. So as any higher honest object, you want it to recover the starting classical like bits it has to generalize. And this indeed happens by just picking n equal 2, so PSL2. And this basically goes back to classical technical theory. And indeed, just by picking this geometry, which is kind of simple, it is a surface with no genus and no boundaries. So basically it's a Riemann sphere. And you have 4 poles. You just pick this kind of very elementary surface. And if you run this machinery, so by taking like an independent basis of paths, or better, of loops on the surface, and you construct these matrices, you do get some 1, 2, 3, and 4. Basically, you get one loop here, one loop here, one loop here, one loop here. You get 4 generators, and they indeed are the K1, K2, K3, K4 of Marta. So we're basically recovering that representation I mentioned was kind of the starting sort of inspiration for this construction. For n equal 3, so really taking advantage of this higher technical theory, and by slightly modifying the surface, really what we do is just kind of glue back one of the holes. So we're now having the Riemann sphere with 3 holes. This is really the choice that is delivering the desired representation. So for the rest, let me just delve into this a little bit more in detail and basically guide you through the whole construction. So starting with the surface, that is going to be this. And here you have it. So we start with the surface and we want to construct the so-called fat graph on the surface. Now, a fat graph is a graph in which, say, the edges are not like single lines in a way, but they are thickened. You have to think of them as sort of ribbons. And a fat graph for Riemann surfaces is constructed out of kind of elementary trivalent vertices. Trivalent in the sense that you have a vertex, and out of it you have like 3 thickened edges. And you have to glue them together in such a way that the fat graph is really leaving over your Riemann sphere, sorry, your Riemann surface, and the faces that you get, so basically kind of the areas enclosed by the graph, must host one and one only of your punctures. For the sphere with 3 holes, this is exactly the case, just by picking 2 of them and gluing them as is. So the resulting fat graph is this one. And you can see indeed that this is one face enclosing one puncture, this is the other, and the outer one is the rest. That is enclosing the third one, the third missing one. So this is the fat graph. And in the next slide, I'm going to take its dual and spit out a triangulation. To do so, just for the sake of a better picture, I kind of cut the fat graph open here and kind of straighten it like this on the left. So you have to imagine that this is really glued together with this. Okay. So the dual of a graph is obtained, say that this is my starting graph. It is the same for a fat graph. So for each face, now this is a face, I have to put now an edge, sorry, a vertex. So let's say this is a face, the outer one here, all that's outside is another face. So let me put just vertex here. And then you have to draw an edge whenever the 2 faces, the 2 original faces, had an edge that was separating them. So for example, this is an edge separating this and this. And so I draw an edge. Oh, sorry. On the dual. And so on. So if we now look at this one, the faces again are this one. Remember that this is kind of close with this. So we have a face here. And then there's the outer face. So I have to locate a vertex here, a vertex here, a vertex here, and then draw vertices, edges according to the previous edges. So these edges is separating this face with this face. So I get this, and then this, this. However, these one are the same because they're glued together with this. This. Yes. And so you see that you get triangles. Like this is maybe doesn't immediately look like a triangle, but it is a triangle. 3 vertices, 3 edges. And it is exactly this triangle here. And this one is this. I'll get back to the fact that some edges are identified in a second. But before doing that, let me basically tell you that I want to, as last thing, associate to some paths or loops over the fat graph some matrices. And it goes like this. So if I take, for example, this yellow one, which is a loop because this is glued back to this. I just need to read off the way it flows through the triangulation and kind of factorize it over transport matrices accordingly. So if this is the top triangle, I see that I flow through it in the fashion of T1. And so I have a T1, and then it goes in the fashion of T2 on the bottom triangle. However, little caveats, we have to think of this as transporting an edge of oriented type. So if I transport this edge and I act with T1, I get the edge flipped here. And if I move it there, I find it incident on this triangle in the opposite way that I would like it to be for T2 to act on it. So I need to kind of flip this, and the theory gives me also a sort of building block to do so, which is this S. So modulo, say up to an S here and there to kind of rectify and make everything consistent in terms of orientation, I get a sort of factorization of all these paths, the blue, the yellow, the red, in terms of a string of transport matrices. Now, I want to basically claim that the C, Y, and R really are the my candidate generators for the representation. In particular, I claim that this stays for J1, this will stay for J2, and this will play the role of J3. Clearly, R is not independent in terms of paths from C and Y, because remember that we want J1, J2, and J3 to be equal to Q. Actually, they're not independent. In particular, J3 is the kind of up to Q, the inverse of the product of J1 and J2, as desired. Now, last step is basically to develop the kind of underlying algebra to run some computations for this C1, for this C, Y, and R. Namely, at the moment, I have no idea the algebras over which these matrices are defined upon. So I technically cannot run any computations and check any relation. I know kind of the algebra on a single triangle, but clearly C is kind of flowing and involving many variables here with others here. So I don't know how they interact together. So to run some computation and really test the relations for the C, Y, and R, I need to really work out the algebra functions on which these matrices are defined. And this is a process called amalgamation. It's exactly what I said before. So I basically need to glue things together and really construct the modular space of my surface with punctures, which is not a triangle anymore, but basically involves two triangles that are suitably glued. So I have now the kind of non-commutative algebra for this triangle, the one we saw before, that sort of higher dimensional torus, and the one for this triangle. But how do they interact? Well, as I said, just by looking at the geometry, say the topology of the underlying fact graph, I see that this side really is the same as this side, same as because of this, this goes together with this. And as I said before, this is really glued together, meaning that this side and this side has to be glued together. Now, the process of gluing together variables is called amalgamation. And it basically requires you to just multiply the variables that basically find themselves on the respective same position when I glue together. So this variable here and this variable here have to be kind of multiplied together, generating, kind of being relabeled into a new variable that in this case is this zy1, and these two form this zy3. By running all these amalgamations and gluing together all things, the result is this quiver here that you see is a little bit kind of different from what was the kind of shape of one of a single triangle. And the only variables, maybe notice, that are not glued together are these ones that are in the center of both triangles, because they really, being in the center, do not lie on any side that has to be glued with anything else. I call this the diamond kind of amalgamated cluster variety. And it is defined as before. So again, all these 8 variables are like free up to the commutations encoded by this very diamond. And now that I have worked out the algebra, I'm ready to kind of have everything I need to run computations and test whether my matrices satisfy any relation at all. The answer, obviously, is that they do. And so maybe finally you can have this C, Y, R is a bit more too complicated, but at least like the shape of C and Y. And they are now 3x3 matrices that live on this quantum cluster variety encoded by the quiver of the diamonds. And the case of C is, you see, upper triangular. The case of Y is lower triangular. And each entry is like a certain polynomial on these variables. And they do satisfy the relations, so they give us a desired representation for the algebra, and in particular, the assignment goes as I kind of introduced before. So C stays for the generator J1, Y for the generator J2, R for the generator J3. Q has to be kind of shifted only because I kind of didn't develop the whole theory of high-dimensional space, and unsurprisingly, it's not exactly compatible with the type of Q that is required from the definition of GDAHA. Maybe to finish, let me point out that I insisted on the fact that we wanted to construct the first representation that had no restriction on the parameters. And this is indeed the case. For C, for example, you have to expect these Eke parameters to play some sort of role of kind of the determinant or like the characteristic polynomial. So being upper triangular, they sit on the diagonal. So these really are the Hecke parameters. Say, for example, this is U 2, 4, 1, because C corresponds to J1. And maybe it's not immediately clear because you see they are, all the U are expressed as some sort of monomials in the Z, but it turns out that this relation can be inverted. So really all the U are free because like they can themselves express the Z variables, and moreover, clearly Q is free. It's here and it's absolutely free. So really this settles the fact that this is really the first representation of this GDAHA that is free from any restriction on the parameter as we originally wanted. Okay, so final slide, just like a take-home message, probably of all this rambling. Let me again basically kind of run again this sort of advertisement for higher technical theory for this slide HTT. So this really basically is a sort of geometric realizer for quantum mechanics. So this modular space really is establishing itself since its introduction as really a strong candidate for sort of geometric realizers of many quantum algebraic objects that are familiar and famous and beloved. What can I say about my work is basically that I can also throw GDAHA into the basket of these quantum algebraic objects, in the sense that, again, GDAHA class 2 finds a geometric realization in higher technical theory, because we constructed the case of HT4, also, again, I mean, the novel realization for the case of E6, and I'm also working on kind of finishing off the package by working out the case of E7 and E8. Okay, I guess I'm spot on time, so happy for that. And really, thanks for your attention. References, yeah.
Okay, great. Thank you very much for a very nice talk. So do we have questions from the audience? Karen, are you raising your hand?
No, I wasn't on purpose, really. I guess I do, just a sort of out there question that you probably won't really know the answer to, but do you know if anyone has looked at the C-star algebras of these guys? Because I know Hecke algebras have been defined for C-star algebras.
It's true, but I think this theory is so young, and I'm talking late 2022,
Okay, yeah,
that
so no one's got around to it yet.
people are still trying to really grasp what this is.
Mhm.
They're doing a lot of advertisement going around trying to explain to people, but it really feels a bit exotic. There's a lot of combinatorial features behind. You
Mhm.
find local system of this geometry, and then it is really a bit weird to see how this can really be having any really relation with proper quantum algebra. So yeah, I think it would take some time to rework out all the possible ramifications that this mammoth work really can have. But definitely, I suppose that they're going to try to attack a more analytic approach eventually. I mean, obviously, because the object that they want to realize have this duality in a way, this kind of double nature. So I suppose that it's going to come eventually.
Then is there, because I mean Hecke algebras is so closely connected to the motivation for categorification, is there there's presumably some categorification going on in the background, or there is a category?
I think they want to achieve something like that. So for example, what I kind of know is that for quantum groups, the whole kind of monoidal structure on the representation category is itself reconstructed in some geometric terms. So basically, all this kind of cluster Poisson property of gluing maps is basically recovering the monoidal structure of the category. So I guess that this is a good green light for a proper interaction with the category, a more categorical approach, I suppose. But again, I don't think they have done anything strictly in that direction yet. I know that there is a categorical kind of approach nowadays to everything in a way, but in particular to quantum groups and things like that. But I don't think they've checked if there is a sort of, it's like sanely categorical realization into the space directly as of yet. Not that I know of, at least.
Yeah, I mean, I guess basically, you understand what I mean? Let's say the work of Zorgel and these people who were taking Hecke algebras and then realizing them in terms of the Zorgel bimodules and so on. But yeah, I guess
names that I've heard, things that I've kind of heard, but I don't have like a working knowledge of that.
Okay.
I have a feeling of what it means, but
Yeah.
with this feeling, I think there's nothing has been done strictly in that direction yet. So I have no, like at the moment, I don't know if the theory as it is able to achieve that. But there might be a similar kind of a categorical kind of lift. But at the moment, I just for like the the interaction I had with the theory, it's already really convoluted as it is. So probably trying to achieve that is going to be quite a feat, I guess.
And then maybe another question I would ask is that so when you were realizing the quantum groups from this Teichmuller approach, you were saying that the quantum groups that you were getting were the standard Drinfeld-Jimbo, but you have, they're not unique. In fact, the Drinfeld-Jimbo, you have a family of them depending upon Poisson structures on the original space, the original group. Presumably, does this encompass all of these different UQ of G's, or is it just the standard one?
I've seen the standard ones for sure. And I think, so having a canonical Poisson structure on this space, I think I suppose you get just a standard one, I suppose. But it might be that we can either the group or the surface that are behind the construction, then you might access others. So that I'm not sure. I'm sure I've seen like I worked out example in which they pick a geometry. So they in particular pick. They basically do this. They pick a disk and they puncture it. Then they put two mark points. Picking this and PGL2, for example, they recover UQSL2 with the standard Poisson structure and all that. But it might be that tweaking the geometry or the group might give you access to others. They haven't checked everything. I don't think I've seen a remark for this really, but it might be that having so many kind of freedoms in a way
Yeah.
might unlock even more. Yeah.
Mm-hmm.
So basically, what they do is that since the whole theory runs on a non-commutative tori, they use some kind of braid actions on the group, on the quantum group, to basically realize the quantum group as a quantum torus algebra.
Okay.
So that is
This is
compatible.
Like braid group action.
Exactly that. This thing braid action. And then just no. Once you have this, you just kind of create a dictionary between the type of quantum tori you get out of this and the quantum tori you get out of Lustig. And by doing that, they essentially realize, say, they basically do a map like this. So let's say that the most stupid case, but which is not stupid at all, but let's say prototypical. This is basically realized into quantum functions over it. I think it is L G sigma, where sigma is this, and G is PGL2, yes. And L is basically obtained out of P by reduction of action of some braid group elements. So then basically this arrow gives you the dictionary of this expressed as a quantum torus and the quantum tori you get out. This is more or less the spirit of what they do.
Okay. And then I'll ask a final question. Is there some way, because I guess what I'm very interested in, a lot of us here are very interested in, is particular sub-algebras of the quantum coordinate algebras that are Q deformations of the functions on flag manifolds. Is there some way that you could understand quantum homogeneous spaces, these sub-algebras of OQ of G?
That's a fantastic question, obviously.
Developing.
That's a good question. I haven't seen anything done directly on this direction, but they have many ways of getting to subalgebra by using geometric term and geometric operations. So that's definitely a good lead to start looking at this. Once you have a realization, then you can play with the geometry. That's probably the most striking feature of it. Sometimes unit geometry is more transparent than just purely abstract algebraic operations. So yeah, by encoding everything in a geometric way, I guess you can unlock a better understanding and more insightful approaches. So probably, yeah, just by using some cutting, doing things like that, you can probably unlock some subalgebras, which typically, in particular representations of subalgebras typically are hard, right? So I guess, yeah, but by doing this kind of operations, you could. But I haven't seen anything directly used in this direction as of yet.
Okay.
Yeah.
No,
thank you. Thank you a lot.
Do you have are there any other questions from the audience? No, that appears not to be the case. So thank you very much.
No, thank you for the invitation. It was always a pleasure to share. And thanks for the question. Oh, meaningful.